Record to the cloud. Okay, I think we are recording and everything.
Cool. Turn my audio off.
Yes, sir. Let's give it a couple minutes for more people to come to. We'll get started in, I don't know, 3 or 4 minutes. Chase, teach me. Dude, Ishan, honestly, teach me. Because, like, teach me why code doesn't work one time, but you don't change the code and the next time it does work. It's really confusing.
So you never got it to work?
I think I did by adding a load account thing, but we're going to find out live together.
Nice.
I think I'm actually running something here. We can find out. Oops, sorry, spoilers. I think I'm running some. Oop, here we go. Yeah, I think I'm running something on accident. And I don't actually want to be. Result canceled. Okay. Yeah, we'll get started. Let's say like 3:05. That seems reasonable.
Yeah. 2 minutes. You turn off the waiting room.
Oh, how do I do that? I have no idea.
I think it's
do privacy in the bottom bar.
Yeah.
Privacy.
Security.
I think, yeah, probably security. Oh, enable
Privacy or security, yeah.
Yep.
Yeah.
Waiting room is now disabled. I didn't know you could do that. I always do. I work as a tutor and I have like Zoom office hours and stuff. And apparently I can just disable the waiting room.
The more you know.
The more I know. It only took me like a year of doing this online to find that out.
I'm still learning new stuff about Zoom. I've been doing that shit for a year now.
Well, we have a recording of Ben swearing online. There goes your political career, Ben.
Well, I was going to run in 2044 or whatever.
2044.
Does that work out?
I think you need to be 35. I don't know when you were born, but probably earlier than 2044.
I think so. I think I will be 45, or I will be like 50 something by then. So
50 something. Oof.
Well, let's see. I'm 24 now, and that's 23 years from now. So I'll be 40. What is that? 47.
Dude,
that's
the math was a little off. I'm hoping your math on your slides is going to be a little tighter.
Wait, hold up. No, that's right. 24 plus 23 is 47.
Yeah, but you said I was like, you're going to be like 50 something.
Well, yeah. Without thinking about it, yeah. That's what I get for not thinking.
I suppose it's technically 3:05. I think this is being recorded. Oh, you know what? I almost forgot again. I literally always forget to send out the link. I also forgot to make the link. So we're just going to say screw the link because I never do it anyways. So we got no sign-in sheet. But let's go ahead and get started, I suppose. You guys can all see my screen and everything, all right? Ishan's going to be like, oh, link for what? Oh, the sign-in. Yo, Ishan, you want to do me a super solid since you also have access to the sign-in link? But yeah.
Okay, wait, where is it? Where is it stored actually?
I think it's in the Slack channel. And then you also have to like make an option. So if you don't want to do that, don't feel bad because it's on me and I haven't done it for any workshops. So I don't think it's that important.
Wow, why do your workshops have 0 people attending, Chase? According to your records, no one attends your workshops.
Someone's gonna fire me, dude. I didn't even know I could get fired from the IEEE technical chair event. But yeah, that's a good segue into the hello and welcome everybody to Introduction to Qiskit. And it's a technical event brought to you by IEEE at UC San Diego. My name is Chase and I am one of the IEEE tech chairs. And today we're going to be going over the very, very basics of creating, simulating, and running quantum circuits, aka quantum computing. Like when people say quantum computing, they mean making quantum circuits and then running them. There's no I don't know. I was always confused because people are like quantum program or quantum circuit, and what's the difference? There is no difference. And when I say very, very basics today, I mean very, very basics. We're going to be going over kind of the syntax of Qiskit and how to get started. And we're not going to be going anything at all into the actual quantum circuits because those get super duper math heavy. And I myself do not know very many at all. So yeah, before we get into that though, I wanted to make this event a little more interactive because if you guys are here, you're probably as interested in quantum computing as everybody else that helped create this workshop. We're all just doing it for fun and because we find it interesting. And it's always fun when we have a bunch of people that are interested in quantum computing to get together and talk about it a little bit. So before we get into actually learning anything, I just wanted to have some discussion, get to know you guys, what you're interested in quantum computing, everything like that. So yeah, there's some prompts here, but otherwise it's supposed to be like, just what do you know? Why are you interested in quantum computing? Why are you here? And I guess I'll go ahead and get it started. I kind of started getting into quantum computing. I believe we ran a workshop with IBM last quarter, and I had no idea about quantum computing before it. But like they wanted to like collaborate with IEEE at UCSD and just like have people come and talk. And I was like, sure, dude, I'll help you host a workshop for that. And then he gave the talk and I was like, dude, that's super cool. This is like the computers of our age. I'm going to be this next Steve Jobs, or I don't think Steve Jobs actually ever did anything for computers, but maybe I can be the next quantum computing Steve Jobs and just get rich and do nothing. The good old days when IBM wasn't radio. Dude, honestly, yeah, way back when we were going to try and do this in collaboration with IBM to learn how to do Qiskit. And then they apparently are super busy collaborating with other people on learning Qiskit. So here we are today to teach it to you guys because I thought it was a cool topic regardless, and we don't have to do it with IBM. But yeah, that's a bit why I'm interested in quantum computing. And I guess one of the main things that like I'm still really interested in quantum computing, and you guys can feel free to like, you know, chime in here. It's meant to be a discussion. But one of the main things I like about it as well is like basically everything you hear about quantum computing sounds like physically impossible because like it's very counterintuitive to our thinking. So like people will be like, oh yeah, we teleported a qubit. And I'm like, what does that mean? How do you teleport a qubit? What even is a qubit? Is it like a bit? Can I just think of it as like a little register? So yeah. But yeah, has anybody heard of any like cool quantum computing theorems or programs or anything they want to share? Random number generating? Prime factoring? Okay, Ishan, you have a workshop coming up about prime factoring, right?
It's just about quantum cryptography.
Oh, how can quantum be used for quantum cryptography? Not give like your whole workshop here, but like, I'm interested because I know nothing.
Okay, I guess I'll talk a little bit about it. Okay, so you know how like to encrypt things, you gotta have two really big prime numbers and then the entire internet is secure because we can generate huge prime numbers that are really hard to factorize. Well, with an algorithm like Shor's algorithm, you can do that. You can factor them easily with a quantum computer, and that's kind of scary. But also, quantum computers can help ensure security as well, which is going to be mainly what I'll be talking about in my workshop later on. It would be about how quantum computers can help ensure secure encryption.
So you're telling me there's going to be like a quantum computing arms race for who can ensure encryption using quantum computers and who can break it?
Potentially.
That's
I can
awesome.
definitely see that happening.
Cool. Has anybody heard anything about like quantum teleportation, by the way? Because I'm still interested in that and I really honestly don't know what's going on.
You know, we were thinking about doing a workshop like that actually next quarter for the Quantum Computing Club. Something about like quantum communication protocols. But I don't know, the math's kind of weird, but it's actually not that bad. If you just go through the like whatever tensor products and stuff, you know, enough algebra, it's really not that bad. So I think we could probably introduce it next quarter for you guys.
Chase,
Ooh.
I'm going to disappoint you. Quantum teleportation is not as cool as it sounds.
Why?
You don't teleport matter, you only teleport information, but you can teleport the state of a qubit using a quantum network.
You teleport information.
That's right. So you can never copy a qubit. The process of measuring it would destroy it, but you can, or let's say, but you can't copy, but you can cut. You can't do Command C, but you can do Command X. So you can teleport information somewhere else.
Dude, that's such a good analogy. You can't copy it, so you can't have infinite copies, but you could take that one and move it elsewhere. Control C, Control X.
With cutting, though, it removes it, but you can do it as many times as you want. You can cut and then paste.
Wait,
but
you can teleport it like multiple places?
Well,
No, I'm
no,
saying
he means on the
literally
computer you can paste it multiple
yeah.
times.
Yeah.
so it's close.
Wait, so but you can't do that with it, because then that would be essentially just copying it, wouldn't it?
Yeah, that's the no cloning theorem, I think.
Okay. All right,
Or no
guys.
clone. I think I don't remember the name of it.
Yeah, that's right. No cloning.
No cloning theorem, yeah.
Cool. Okay.
It's like a Pokemon Center, you know. You put your Pokemon in the Pokemon Center, and then you can go somewhere else and withdraw it. You can't withdraw it multiple times.
You're telling me that there's never been a Pokemon hack that like you duplicate Pokemon by doing that? Because like
there most definitely is.
yeah, there's got to be. That's probably where all like the duplicated Pokemon come from. Or isn't it like when you put it? Isn't that the computer you're talking about, where you like put them in a computer, and you could like withdraw them at other Pokemon centers? This is
Those are, like,
totally
boxes?
separate.
Mhm.
You need a Pokemon to sacrifice. Oh, geez. Yeah, that's what, is that what quantum teleportation is? If I were to teleport myself somehow, does it like get rid of me? All right, this is not a philosophy meeting. I don't want to get into this. It's going to get too deep. I'm going to be sat up at night, like what's going on? And then here's some more food for thought for people. We got this image over here, and I'm making no claim that this image is accurate or not, but it says that binary bits are a bunch of zeros and ones, right? And quantum bits are this, I think that's a Bloch sphere, or is it a Q sphere? I think that's a Bloch sphere, right?
Yeah.
So if a binary computer, digital computer is a bunch of bits that you can use, what would a quantum computer look like?
You mean like what would it physically look like?
Yeah, dude,
Because
does it look like that atom over there according to that image? Is this accurate?
Nope. It's not even what an atom looks like.
Whoa. Now you're getting into quantum physics? Well, that's what we're here for, aren't we, huh?
I guess.
Actually, today we're not going to be doing any actual quantum physics, right?
this is going to be programming, right?
Yeah, and very basic programming at that. You don't actually even need to have like programming pre-knowledge to do the stuff we're going to be doing today. It's almost, Python is really nice in that pretty much everything you do is basically just like the English of what you would think it would be doing. So that's pretty cool. So yeah, it's pretty much been, this is welcome to quantum computing, very informal meeting, but just everybody from Quantum Club talking. But there's some new faces here. Do you guys have any input on this quantum anything? There's a lot to talk about, so that's a little intimidating of a prompt. Retrospectively, I should have got more water before this workshop. Yeah, has anybody heard of any cool applications of quantum computing? Because honestly, in terms of my interest for quantum computing, I literally don't at all care what it's going to be doing. I just want to know how it works because it's very weird. But does anybody like here because they're like, I want to learn how to do this with quantum computing? Any specific interests?
Well, you can do very good material science with quantum machine learning. Very good material science. That's a
Best material science.
the best material science.
What does that mean? How does it help?
When like all sorts of physics simulations you need to do to figure out how materials will behave under heating or under light or under mechanical stress are really, really computationally intensive. It takes a ton of supercomputer time and money to simulate. And the idea is that if you could use quantum computers, then you could simulate stuff a lot faster. And considering that supercomputer time is like extremely expensive, you could actually save a lot of money and do these computations a lot faster.
Oh. And that scales well with quantum computing because their whole thing is like parallel computation, right? So would you represent like one molecule in the atom with like one qubit, or how would that work?
Yes, that's right. Actually, so the stuff I've seen on this topic so far is that, yeah, some of the atoms in the most active region of the material will be represented by a qubit. And then that way you can simulate the most difficult quantum parts of the material with a quantum computer.
Oh, that's pretty cool. So yeah, any other interests? I have an image up here that I pulled up. I think this is very similar to the material science you were saying, but I believe it's about the development of like drugs. Like you can see how they would interact. I'm not sure if you're simulating like the actual synthesization of the molecule or whether it's like the interaction in the body, but I've heard that's something good for quantum computing. Does anybody know anything about that? It's okay. I won't bust you if you come on the stream and say, yeah, I know a lot about drugs, by the way. That's even though this is recorded and going on YouTube, just don't worry about that.
The old Walter White make a new strain of meth or something.
Yeah, he was a chemist, but I'm a quantum computist, and so I got to make some other kind of new show coming out with a different drug.
That's got to be the word now. A quantum computist.
Quantum computer. What do they call it? What is it? Quantum scientist, maybe? Do they have a name?
I don't know. I mean, the field is called like quantum information, so quantum information.
Technically, Heisenberg still fits.
Oh,
yeah.
Nice.
Actually, it fits more in this case.
Definitely fits more. Although, guys, I've never watched. Was it Breaking Bad? Heisenberg's like his helper, right?
It's his like his alias.
Alias.
Oh, yeah. I've never watched. I feel like Breaking Bad's gonna make me sad if I watch it. It seems like it's too intense of a show for me.
It is really intense. It doesn't really let up, you know. Like it's not like the show. There's shows that are intense, but like we'll have like more lighthearted moments and stuff. But Breaking Bad's pretty much just like.
So we've been talking, and by we I mean honestly mostly me, for a couple of minutes here. It doesn't sound like we have too many people with pre-background knowledge of quantum computing outside of the people that have spoken, but everybody is here to learn about Qiskit, so let's keep it moving forward. And before we get into the actual programming of Qiskit, we're going to cover some super basics, just so you have an idea of what we're actually doing in Qiskit before we get into the programming. So for that, Ben, take it away.
All right. So can you guys hear me all right?
Sound good to me.
Cool. Yeah, so if you guys went to the workshop last week that we did for the Quantum Computing Club, which I think is a lot of you guys, you'll have seen this stuff already. But I'm going to be doing a much more brief kind of okay. But yeah, I'm going to do a much more brief kind of introduction for you guys. We're not going to go over like the Kets. So like we went over like and let me annotate real quick. Like we went over this Ket notation where you have like the 0 plus 1 or whatever right here. We're not going to go over that today because it's not even really necessary to get through kind of what what we need for the program that we're going to run, right? So there's really only 3 things that we need to know for this program. The first thing is we just need to know that like a qubit is basically just a vector, right? The second thing we need to know is that the square of the amplitudes of those vectors. So if we have some vector, alpha, beta, the square of those numbers right here is the probability that you're going to get the result there, right? You know, probability of getting some result, let's say 0, for example, right? And then the last part that we're going to go over is just what a quantum gate is. We're going to learn the Hadamard Gate, which is the same one we kind of went over last time. And that's pretty much going to be it for us. So it's going to be a little bit shorter. And we might might worry even less about the complex numbers here. So just to get started, I'm kind of going to do the same thing we did last week, right? And this will be good review for you guys that you know might want a little bit more kind of review on this stuff. So like I have some vector in a so I have some vector in a two-dimensional vector space. So I'm in R2, right? And I think you guys have probably seen R2 before, right? You know, even in just like, you know, basic geometry or whatever. It's just just 2D plane, right? That we're totally used to from you know, years and years of math. Yeah, exactly. R2, D2, yeah. So we have some vector here, right? And that vector is just represented. It just has two numbers, right? And we'll call those A and B, right? And those are real numbers. So A and B are in the set of real numbers, right? And that's it, right? That's pretty much all we would need for like R2, right? So we're dealing with a vector space that's really similar, except it's actually these numbers are going to be complex here, right? So we're dealing with, instead of R2, we're dealing with C2, right? So we're going to have, you know, some number alpha and some number beta, right, in our vector, and alpha and beta are going to be complex numbers here, right? We're not going to worry too much about the fact that they're complex numbers, but that's just something that we kind of need to know. That's the kind of difference here. And that's pretty much it. We have this thing called the normalization condition, okay, which means that if you take the magnitude of this alpha here, and you square it, and you add it to the magnitude of this beta here, and you square it, you're going to get 1, right? So in R2, and I think I asked this last time, so if you were at last week's workshop, you'll remember this. What is the set of vectors such that the components add up to 1 when you square them like this? It's a certain shape. Let's see if any of you guys can figure it out. Jeez. So not quite. So a square would be a little bit different. All right, you guys are just giving me shit. There you go. Daniel's got it. So the one of you guys that didn't go last week and actually had to think about it. So yes, a circle is going to be this shape here, right? So a circle is just the set of vectors such that the amplitude squared add up to 1, right? Since these are complex numbers, it's going to be a little bit different. It's actually going to be kind of like a sphere kind of thing. But we're actually going to only think about real numbers for today, though. So just keep in your mind that these are complex numbers and it's really a little more complicated, but we're just going to think about real numbers, and that's going to make this whole process a little bit easier. So let's imagine the alpha and beta are real numbers, right? So we have this condition then that alpha squared is the probability of getting, let's say, the result 0. So it's okay if that doesn't make sense at first. I'm going to explain that in a second, right? And then beta squared is the probability of getting some result, let's say 1 here, right? So what that means is, I guess here, no, you're all good, Chase. We don't hear any noise.
Awesome.
So yeah, so basically what we're saying is okay, some vector right here, let's call that vector 0, okay, and this vector right here, let's call that vector 1, right? And you know, in quantum computing, we use this thing called Ket notation here, so we write them in a certain way like that, right? And we call those kets, but we're not going to worry about that for now, right? But it's just, we have some outcome right? So a vector, this vector right here, that's fully on the x-axis of length 1, right? If our qubit is in that state, or if our qubit is in the state 1, 0 here, then that means that our qubit is the classical bit 0, right? And if our qubit is in the state 1 right here, right? So that would be the vector 0, 1. That qubit is in the classical bit state, right, is equivalent to the classical bit 1, right? So just like a classical bit, qubit can be in 0 or 1, right? And then we're just going to abstract it a little bit, and we're going to say, okay, but a qubit can also be in a weirder state. You know, for example, this state, this is like, some state alpha beta. It's not 0, right? Obviously, and it's not 1, right? It's actually a completely different type of state. Okay, and the way that you can think about this is like, if you've ever heard of like Schrodinger's cat, right? You have a cat, you put it in a box, you have some event that has a 50% chance of occurring, right? And then when that cat is in that box, and if the event occurs, the cat dies, right? So that box, when it's closed, right, and you don't know if the event occurred or not, we actually say the state of that system is in what we call a superposition. So that cat is in a superposition of dead and alive. It's not dead, it's not alive, right? It's something in between. It's in a weird quantum state. That's kind of all we can say about it, right? There's different interpretations of what that actually means, but that's basically the gist of it, right? So that cat is, so like this state here that I was showing in a second here, like that would be, that would be the equivalent of that cat being kind of, in some superposition of dead or alive, right? And that's basically the gist of it, right? We're just gonna, undead, exactly. This is a zombie cat. So, we're just gonna focus on this first quadrant here, because it's a little bit easier to conceptualize. So let's look at this first quadrant, okay? And let's look at some vector here, and this is going to be, alpha, beta, right? So alpha squared, and we're going to think about these as real numbers just for now, right? But it would be the magnitude here, is the probability of getting, and let's say we call this state 0, we call this state 1. So then alpha, which is this amplitude here, right, is going to be the probability of getting that 0 state, right? So let's say we had a cat in the box, and that cat in the box is in some weird state that's not, dead or alive, right? It's in some combination of the two, right? So the probability that when we open that box, that cat is going to be dead is just going to be the square of this amplitude right here. It's okay if this stuff doesn't really seem to make sense. It's just really new, and it's weird, and it's not necessarily conceptual, right? It's just a weird abstract mathematical representation of some system that we have, right? But that's basically the gist of it. If you can even just tell yourself, okay, here are the rules. I have, an arc in the first quadrant here, even, just to really simplify it, and I can be in any state, between 0 and 1. If I'm in a state up here, obviously, like, I'm more likely to observe a 1 if I observe my qubit, right? If I measure it, if I open that box there, right? If I'm in a state like this or something like that, right? I'm much more likely to get a state 0 if I measure that qubit, if I open that box there, right? So that's basically it, right? It's just a weird new way of thinking about this stuff. It's not necessarily going to conceptually make sense. I'm not, unless we like went over photon polarization for 20 minutes, which we're not going to do. But basically, qubit is a mathematical object. We represent it as a vector in a complex two-dimensional vector space, but we're just going to even imagine it in a real vector space just to help us conceptualize it, right? And how far that vector is from the, and then it's of length 1, right? So we have this arc right here, and that's the set of all vectors of length 1 in the first quadrant, right? And then just those amplitudes, right, just represent probabilities, right? The squares of them are probabilities. So if we're closer to this zero axis right here, or we're closer to the positive x-axis, right, then we're more likely to get this result when we measure our qubit. If we're closer to this one state right here, then we're more likely to get that result. If we measure our qubit, we can actually be in an exact superposition of both. So this is the point. What would this be, like 1/√2 times 1, 1, right? So that point would be, like as if we can even imagine it as a coin that's like spinning through the air, right? We measure that coin, right? We're going to get a 0 or a 1 with equal probability, right? So I guess we can go on to the next slide. I guess we'll do 2. Yeah. So we got the measurement principle. So the measurement principle is just what I was talking about, right? Where just the amplitude squared here is the probability. And when we measure something, right? If we open that box, we're not going to be able to observe that weird quantum state, right? We're going to either see the cat as dead or alive. So that's basically the measurement principle. Is once you open that box, once you measure your qubit, you're going to get some result with probabilities that are determined by your amplitudes here, right? Same thing with that cat in the box, right? And then last of all, I think the next slide we'll talk about quantum gates. So for this, we're going to need to know a little bit about matrix vector multiplication. Okay, if you haven't really seen that, I think they go over it in like pre-calculus for like 5 minutes. But if you haven't taken linear algebra, basically you can have a matrix, A, B, C, D. You can multiply that matrix by a vector, and that multiplication here, you can think about it as just kind of changing that vector, right? So if I have like some vector and I multiply it by a matrix, we call that a linear transformation. And what that's going to do is that's either going to keep the vector in place, it's going to scale it down, it's going to move it over here, it's going to do something to that vector, right? And that's just, if you haven't seen that before, that's totally fine. It's just a way that we can perform operations on vectors, right? So just like we have classical gates, we have like the NOR gate, the AND gate, the X gate, or the NOT gate, right? We have all these classical gates. So if you've taken that, I think ECE 25 or something like that, and there's the C equivalent 16 or something. You've seen those classical gates, but basically classical gates are how we do operations on regular bits. So we have a string of 1s and 0s. We can run all those 1s and 0s through a bunch of gates, and we can perform logic. We can say, okay, if these two things are both, if this is a 1 and this is also a 1, then this thing is going to become a 0, stuff like that, right? The quantum equivalent of that is a quantum gate, and what that basically is it's just matrix vector multiplication. That's all it is, right? So for example, we have the X gate, and the X gate is just 0s in the diagonal, 1s in the anti-diagonals here, right? So we multiply this gate by some qubit A, alpha beta. It's just a vector, right? That's just going to give us, and then I guess I'll give you guys the opportunity to see if you can figure this out if you didn't attend my lecture or the last week's workshop. Figure out what that's going to give you. No takers? Or I'll give you another 5 seconds or so, and then I'll just give you guys the answer. All right, so you have to do multiplication, yeah. So we got 0 times alpha plus 1 times beta gives us a beta here, right? And then 1 times alpha plus 0 times beta gives us an alpha here, right? So all this X gate does is it just flips our qubit, right? If you haven't seen this multiplication before, you haven't taken linear algebra, that's totally fine. But just kind of keep in mind that that's kind of how it works, right? Is we just multiply matrix by vector. That represents operations that we can physically do on qubits, right? So here's an example. We have, let's see this gate, right? So this is called the Hadamard Gate. Okay, this is a really important quantum gate. And this is going to be 1/√2, and that 1/√2 is to make sure we keep our normalization condition, right? Or normalization condition here, right? Because we have alpha squared plus beta squared. is equal to 1, right? So our matrix, if we multiply our vector by matrix, this still has to hold, right? So, whoops. So as we can see, pretty obviously, this thing is normalized, right? Because if we just switch these, the same condition is going to hold, right? This one is a little harder to see. We're not going to worry about it, but just keep, that's why we have that 1 over root 2 there. So here's our Hadamard gate, 1, 1, 1, and then a -1 right here. So if we multiply that gate by our state, by let's say we take that gate and we multiply it by what we call the 0 state. So that's just a vector on the x-axis there, right? That is going to give us 1 over root 2, right? Because we keep this coefficient here, right? And then it's going to give us 1 and 1 there, right? Right, so we got 1, 0, right? And then 1, 0, right? So that's going to give us that vector right there. That vector would represent like an even coin toss, right? So you can imagine, pointing straight out at 45 degrees, right? Equal probability of getting a 0 here, equal probability of getting a 1 here, right? So this is a really important state. When we observe this state, we take the state and we observe it, right? We're going to get a actually random result, right? It's not going to be, it's not going to be semi-random. It's not going to be according to some sort of rules that we can predict, right? It's actually completely random, right? And that's really important because classical computers can't provide that kind of randomness, right? We call classical computers pseudo-random. They're not actually random. And I know we talked about this last week, so this is a review for some of you guys, but that pseudo-randomness, right, makes it really hard to generate truly random numbers or a truly random distribution on a classical computer. Quantum computers, however, can, just by observing these states, right, if you take a cat, Schrodinger's cat in that box, and that cat has an equal chance of being a dead or alive, you open that box, you're going to get a truly random result, right? And you can imagine, let's say you have, and let's say maybe the cat's going to be asleep or awake. Let's say it's like nerve gas instead of, it's not going to kill the cat. Okay, so we're not going to kill a bunch of cats. But let's say we have 8 boxes of cats, right? We open each of those boxes, and the cat has an equal probability of being dead or alive for each of those boxes. We're going to get 8 random bits, right? So let's say we call 1 alive, and we call 0 dead, right? So we're going to get, dead or I guess, asleep or awake, right? We're going to get like, awake, asleep, 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 awake, awake, whatever, right? With a purely random distribution there. So that's a really important result. And then we're also going to have our Hadamard gate applied to the 1 state. So that's going to be basically the other basis vector. That's going to be the one pointing upwards here. Is going to give us 1, -1 here, I believe. And so as you can see here, when you square these amplitudes, right, you're going to get the same thing, right? You're going to get alpha squared is going to be 1/2, and then beta squared is going to be 1/2, which means you have, again, a 1/2 probability there. So that's pretty much it for what you guys need to know. I know that was really quick. I try to go over it quickly so it gives Chase some time to really present the rest of this workshop. But that's basically the gist of it. It's okay if some of this stuff doesn't make sense. The key takeaways, though, are basically quantum state, a qubit, is just a vector, right? That it's a vector of length 1, right? It's complex, but we're not going to worry about the complex part, right? We're going to think about just real vectors just to make it easier for ourselves. So it's just a qubit's a vector, right? Those amplitudes, so that A and B or that alpha and beta there, right, represent the probability. So if you square those, you get the probabilities of getting, that up state, the 1, we're calling that, right? Or that the horizontal state, right? 0, we're calling that. So you can imagine like Schrodinger's cat, we're, taking some state 1 1 over root 2, right? And we observe that state, and we either get the 1 state or the 0 state or the 1 state, right? So that's basically the gist of that, right? And those are going to be with equal probability because these numbers right here are equal here, right? And then quantum gates are matrix vector multiplication, which is, even if you haven't seen that before, right? That's okay. We just have to basically remember that if we apply the Hadamard gate, and specifically if we apply the Hadamard gate to the 0 state, that's going to give us a superposition. It's going to give us a coin flip, right? It's going to give us 1 and 1 there, right? Which means the probability of getting each of those states is equal. And so that's how we get some quantum coins. So lastly, yep, and we're going to be dealing with multiple qubits, but we're not going to be worrying about the multiple qubit kind of mathematical structures. There's some tensor products and stuff. We're not going to even think about that stuff though for today. We're going to basically treat each of those qubits by themselves. So I guess Chase, I could go over the kind of how this circuit, or here I'll do this. I'm going to go over like a very, very basic quantum circuit with just 1 qubit. So I'm going to take a qubit. I'm going to start it out in the 0 state, right? This is the 0 state here. I'm going to make this look better. So this is the 0 state right here, right? I'm going to take that qubit. I'm going to put it through a Hadamard gate, okay? So remember this vector matrix multiplication. Now I'm going to have a 1 1 state, and then I guess I have a 1 over root 2 multiplied by that, right? Then what I'm going to do is I'm going to measure that qubit. So we represent that with this little kind of measurement gauge looking thing, right? And then I'm going to either get a 0 state, right? Or a 1 state with equal probability, right? So this is basically a random bit generator. That's all this is, right? I guess that's pretty much the gist of the circuit we're going to be doing. We're going to be constructing today, right? We're going to basically
the entire circuit, Ben. That's it.
Yeah. So I guess Chase will maybe go over a little bit more about what's actually happening, or what the actual program is going to look like. But I think we're just doing eight bits of this, right? So we're just doing this 8 times, and we're generating 8 random bits. So we basically have an 8-bit random number that is truly random. That's not pseudo-random, is actually by the laws of physics random, which is an important result there. And then we're measuring all those qubits, right? So we're just doing this exact thing 8 times. So
All
that is basically it there. If you guys have any questions or anything, feel free to ask. But I try to make this as simple and as clear as possible, even though it's a really weird kind of new mathematical thing that we're dealing with. So,
take a minute. Anybody? Any questions?
I think even if you don't understand what I talked about before, right? The key, if you can just understand, I start out in a 0 state, right? I apply some operation that gives me, Schrodinger's cat is either dead or alive, right? We don't know. It's still in the box. Then we open the box up and we get either a dead cat or a live cat, right? Just even that idea is going to get you through the rest of this workshop here. So.
All right. It doesn't sound like anybody had any questions, so let's move on. So today we're going to be going over how to program in Qiskit. Specifically, we're going to be doing this in what's called the IBM Quantum Experience, which is basically just kind of like a cloud platform that allows you to, there's a lot of nice features. So the first and main and biggest draw is that it allows you to run your quantum circuits that you've made in Qiskit on actual quantum computers. So in this picture, you can see there's some names of the computers. And I took this screenshot, I think, a couple days ago. I'm not going to lie to you guys. Actually, running it on a quantum computer takes quite a while because, as you can see, there's a total amount of jobs pending because everybody can do this if they want. So it takes a while to run on the quantum computer, but it doesn't cost anything. You literally just join a queue and wait until it's done. So that's one really huge draw, is that you can literally do this on like actual quantum computers as if you were doing like real research, which is very cool. One of the other features we're probably not going to touch super much on today, because today's focus is about like learning to program in Qiskit. But you can, in addition to making your circuits in Qiskit via code, via Python, you can also just do like a Scratch-esque drag and drop like block diagram of circuits, where you have all like the different operations. Each one of these little blocks would represent an operation on a qubit, aka a matrix multiplication that Ben showed us. And you can actually like drag and drop them between qubits and everything, and make your circuit that way. Again, we'll go show the interface for that, but we're probably not going to do it. And then the final thing is it's also just a really nice place to learn Qiskit. It has a built-in place that we're actually going to be writing all our code in to actually like write and test your Qiskit code. And it has a bunch of different like tutorials in different areas, and very nicely commented code to like, here's what we're doing, here's why we're doing it, and so on. So it's a really nice like website. It's totally free. Well, totally free outside of they get to harvest data from you because you have to sign up via an email. And I think you have to put like your name and stuff too. So if you're anti-government, staying off the grid, probably not going to like this. You also probably shouldn't be in this recorded Zoom call. But otherwise, it's very easy. It took me about a minute to set up the account. So yeah, that's where we're going to be doing everything. But let's go ahead and get into the actual basics of the circuit, why everybody's here. So the first thing to get started with a quantum circuit is you need to import all the tools that come with it. So Qiskit is the package we're going to be working with, the software development kit from IBM that allows us to make quantum circuits, simulate quantum circuits, see how they look, see the results. It's very, very well built out. And at the end of this, we will also have, Qiskit is actually an open source program, so you can like contribute to it as well. In addition to all the features, if there's something you want to do, but it isn't there, you can make it yourself. But yeah, so the first step to actually writing a program, actually, let's take a question. So this question in chat, where are we doing this? We will be doing this in the IBM Quantum Experience. I will show you the notebook in a second after we get through this import slide. But yeah, to get started, you need to import a bunch of stuff from Qiskit so that you can actually use it. So there's some default like things that are nice to work with when we're working with Qiskit. So by default, oh yeah, I should have linked that, sorry. So Daniel sent the link to the Quantum Experience. Like I said, it takes about a minute or two to set it up. You guys weren't expected to come to this workshop with anything installed or any pre-knowledge, but we'll be showing how to do it step by step. And then we should have some time afterwards if you guys want to stick around and need any help to get started in the Quantum Experience as well. All right, but back to the imports. So there's some defaults we like to do. So just importing Numpy. Numpy is really nice for manipulating like arrays and just a lot of large data, which these quantum circuits, they're not going to be too large of arrays if you consider the array as like a qubit. But it is nice to manipulate with, as well as I'm not actually 100% sure what matplotlib inline does. I believe it's something to do with showing your results like after you simulate a part of your circuit. I think it makes the output like nicely inline, but it's a good default to have, so we're going to throw it in. And then otherwise, this is like the actual meat and potatoes. So the biggest important one is the quantum circuits import. So from Qiskit, you will import quantum circuit. And that opens up a ton of functionality to creating and like manipulating circuits. Pretty much everything you would need to do in a quantum circuit, you're going to be doing there through that library. And then we also want to be able to simulate and visualize everything we're going to be doing. So there's some more imports there. There's IEEE, which is the backend for Qiskit that allows you to simulate, and also a function called execute that does the execution for you. The import is of great import. Thank you. And then finally, all of this would be somewhat useless if we weren't able to actually visualize what's going on with our circuit. It would just be giving us like a bunch of like random complex numbers that don't really mean anything to us. So in order to see like basically the probabilities of our results, we will be plotting essentially a bar graph of all the different options of the outputs that could have happened, and then the probability of each one, which we'll be doing from Qiskit, the visualization package in Qiskit, the function called plot histogram. And the last one running on a real computer we'll get to, but it'll tie very nicely in. So let's just go all the way. No, sorry. One of these tabs is the home. We'll just make this one the home. So this, wait, you guys can see my whole screen, right? Anybody?
Yep.
Okay.
Yeah.
So you can see the homepage. So this is the homepage of the quantum experience. You can see it's me, Chase Bastian. So there's nothing super relevant on this homepage besides these are all the quantum computers that you're able to use. And they also tell you like how many qubits they have because that limits what kind of programs you can run on them, as well as how busy they are. So they look extremely busy today. Look like 7,000 jobs. So we probably won't actually have enough time today to physically run something on one of these computers, but I do have some results I did before. And I actually went on a walk for how long they took. So I don't know exactly how long they took, but like upwards of 10 minutes. So probably won't wait around for that today. And here's, you can see like all the lists of jobs you've done in the past and so on. And then there's a ton of other features. So here, I believe is the, okay, these are the actual things. This is what I was looking for. This is the graphical interface for doing the circuits if you want. We're not going to make our circuit in here, but it's literally as easy as like drag and drop. Oh, I want to measure that one. So you can literally just drag and drop and it does like, this is a Q sphere. We're not going to go over what that means because it's not really relevant for today, but it's a nice tool for visualizing what your circuit does. And then this also shows you the probabilities and the states and everything from the circuit you're live updating. So that's a really cool tool. But today we're here to learn about Qiskit. So the way to do Qiskit, like I was mentioning, is the IBM Quantum Experience actually has a built-in place to do your code. So here is where all your tutorials are. And if you wanted to actually create your own code, you would make your own new notebook. I just have that open in another tab here. So the first thing we're going to do is import everything that we just went over. So we have all the stuff to create our circuit. I added some extra inputs about quantum registers and classical registers. It's literally just, if you guys, most of you are probably familiar with registers from computers. It's the same idea, just quantum register would be qubits instead of bits. And then all the tools as well to simulate, as well as visualize our circuit. And then this we will be getting to later on how to actually run it on a real computer. More than likely, we won't actually be running it today because it takes a while. But here's all the imports, nothing fancy going on. We just got to load it so that everything is there. And we can use it in the future. So that's all the getting started out of the way. Because I know when I start programming something and working with new packages, I'm always like really intimidated. Like, what do I even need to do to start? So this is all the stuff you'll need to do to start. And then next up is the main meat and potatoes to today. Oh, my Irish ancestors are smiling on me. So most of what we're going to be working with is that import of the quantum circuit, because we're going to be working on making a quantum circuit. And so the syntax for the making of a quantum circuit is very straightforward and makes a lot of sense. Once you've imported it, you're literally just going to do quantum circuit. The first number that you input, it can either be an integer or one of those quantum registers that we were just talking about. It specifies the amount of qubits for your circuit. And then the second number can also either be an integer or a register. And it specifies the number of classical bits. These are usually used for output of your circuit. And so once you've initialized it, you'll give it a name, say like my quantum circuit equals, and then quantum circuit with the numbers you want to create. And then you can think of that quantum circuit, my quantum circuit that you've named or whatever you want to name it, as an object that you can then do operations on. So there's a ton of built-in functions to the quantum circuit import. Most importantly, like all the gate operations that Ben was going over, like Hadamard gates, X gates, stuff like that. And they essentially, you can think of it as your quantum circuit as an object. And then by doing the line of code of like you're adding a gate, like my quantum circuit.h is you're adding a Hadamard gate to your circuit. So it's pretty straightforward. You don't need to really know too much about coding to do it. And that's how you go about creating them. So the goal of this workshop is not going into specifically like how to create quantum circuits to do something, because that gets extremely math heavy. And I am no expert at all. I would not be able to give a workshop on that. So today we're going to be making, like Ben mentioned, a very simple quantum circuit that essentially only involves the Hadamard gate. And it's good enough to make us a random number generator. But if you are interested in more complicated circuits, there will be some resources later that you can look into. And honestly, you'll be on the cutting edge as soon as you get through the Qiskit tutorial. So a little past the scope of this. But yeah, so let's go ahead and look at how to do that in our actual program. So here, we're going to make a function that's going to return the circuit. So That way we don't have to essentially make a circuit every single time we want to do something new with it by doing all these functions. Instead, we'll just call this one function name that will return the circuit for us. But to get started, the actual making of it is very similar to essentially what you would do the first time you make your circuit, except we just want to be able to reuse it. And so to do that, you would just name your circuit. So in this case, we called it circuit. And then you would call quantum circuit and give it the amount of qubits you want, and as well as the number of classical bits you want. So since this is a function, it takes in one input, and that input is the number of qubits and classical inputs, or classical bits. So then we pass that into quantum circuit, and it will make a quantum circuit with that number of qubits and that number of classical bits as outputs. And then for us today, as Ben was showing, all we want to do for our bits is apply a Hadamard gate and then measure them. And that will give us the completely random function that we want in order to make a random number generator. So in order to do that, we need to apply a Hadamard gate to every qubit in our quantum circuit. So this is a little bit of coding. It's not too complex, but hopefully you guys have seen for loops before. But otherwise, what this line of code does is literally just for every I, so that's just an iterator, but you could also think of it just as a qubit. So for every qubit in our circuit, we want to apply a Hadamard gate. And the way to do that is we do the operation on our circuit. So we think of our circuit as an object. And to apply a Hadamard gate, we do .h, which applies a Hadamard gate. And the one input there is the qubit we want to apply that Hadamard gate to. So if we want to apply a Hadamard gate to every single bit in our circuit, then for every qubit in our circuit, we're going to do circuit.h, which would apply the Hadamard to that qubit. So this runs through every qubit in our circuit and applies a Hadamard gate. And then the only thing left to do to make this random number generator, after we've set up the superposition with the Hadamard gate so that we now have everything completely random, is now we need to measure it, because then we measure it and it'll give us the actual random number. So the way to do that, similar to the Hadamard gate, is for every single qubit, we now want to measure it. And no surprise, it's very straightforward. The way to measure a qubit is .measure. And then the syntax for this one is a little bit different. So it measures the qubit is the first input, and then the second input is the classical bit you want the measurement to go into. So for our circuit, we're going to measure the first qubit or the 0th qubit or whatever I is, and then put it into that classical bit. So for example, if I want to measure the first qubit, I would do circuit.measure 1, and then I would put it into the classical bit 1. And then that is the entire functionality. Again, this is a very simple circuit, but it's just showing some basic features of Qiskit to get you started when you actually want to make complicated circuits. So that would be the entire ability to make the random number generator. And then just because this is a function and we want to be able to reuse it, we return that circuit. So when we call this function, we would just call random number generator with however many bits we want. And that would return a quantum circuit that measures into the amount of qubits into the amount of classical bits, a random number generator. We can kind of abstractify. Give me 1 sec to take a sip of water. So that's most of the functionality of quantum circuit. Ours is very simple. There is a ton of built-in functionality for whatever you want to do. If you think there's a gate that you need to apply, it'll probably be built in. And if not, there's probably a way to make the gate that you need. So the quantum circuit's the real meat and potatoes of this. Love that phrase, by the way. So next up, after we've made a quantum circuit, I guess before we move on, is there any questions on anything about creating a quantum circuit or how to apply any gates or anything to them? Okie dokie. So then after we've made our circuit, it makes sense that we want to see what the circuit looks like and then what's it doing, right? So the way to see what our circuit looks like, there is a built-in function in the quantum circuit, I guess, package, or I don't know what to call that, called draw, that'll show you what the circuit looks like. And it'll actually use, I think, exactly the same, like how it looks in that thing in IBM Quantum Experience where we did the drag and drop. So when we do that draw function on our circuit, it will show us essentially what that block diagram we would have created by dragging and dropping looks like. So in this case, we would just need to create a circuit by calling our function. So this will make an 8-qubit random number generator. So 8 bits of random bits. That didn't make sense. It'll have 8 random bits. And then if we draw it, we'll see what it looks like. So just like I believe Ben started drawing out when we looked at it. So for every qubit, we first apply a Hadamard gate, and then we have this little measuring box that means measure that qubit. And then those measurements output to the classical bits down here. So this is a very simple circuit, and it doesn't really tell us a lot because it's very simple. But if you had a complicated circuit, this draw function would tell you a lot about what your circuit's doing or maybe where you went wrong. So yeah, that's how you would draw a circuit. And then how you would visualize what a circuit's actually doing is first you would actually have to execute your circuit. So we will get into how to do that in a second. And then you would plot the histogram of your results. And so this histogram is going to have every single state of your circuit that you could have. It'll show you the probability that that state did occur. And so the only way that this is really relevant is when we simulate our circuit, we need to simulate it a lot of times because it's going to be completely random to see what its distribution of random outputs will be. Because if you ran it just once, you'll get like one output at 100% probability, which makes sense because if you only ran it once and you only got one result, the way to interpret that is that's 100% of the results. But if you run it a lot, you'll get your distribution of what's actually going on. But we will get into that after we show how to simulate the circuit, then we'll get into visualizing it. So next up, we have our simulating. Oops, I didn't mean to hit share. Get back into present mode. So to simulate our circuit, there is a very nice tool built into Qiskit called IEEE that does all the backend simulation with us. And it's really nice because you could do like fully theoretical simulations where you would get like the theoretical probability, or you can also simulate things like random noise or just like actual like true randomness where it's not going to perfectly give you a 50-50 split by specifying a bunch of stuff in the simulating environment. But we're not going to get into that because that's pretty complicated today. We're just going to see how to very basically simulate some stuff. So we already set up in our initial imports getting this IEEE into our thing. And then we need to set up a backend for simulating it on. So there's a couple different backend options today. The one we're going to be using in our simulation is this Qasm Simulator. And this is the one, so the state vector simulator is like the purely theoretical, and it would give you like perfect, like, oh, 50% this, 50% this. The Qasm Simulator gives you like an actual, like, it tries to simulate real life, so it's not going to be a perfect distribution. It'll get closer and closer to what the perfect distribution is based on how many times you run it. But for a given amount, it's not going to be perfect. And this is also the one where you can specify like different like error things like thermal noise and stuff like that, which we're not going to get into today, but it does have that function, which is very cool. But to simulate it, we need to create our circuit and then create a backend for that circuit. So today we're going to be using this Qasm simulator. And then we need to actually simulate it. So this simulate uses that execute function we imported before to actually essentially run the circuit. So let's go ahead and look like what that does in our Python code. So the first thing we need to do is set up our circuit. So in this case, we're doing a 2-qubit random number generator. And the reason we're not doing 8 is because it'll look really confusing because there's going to be a ton of outputs on the bottom because there's a bunch more states. But with 4, it looks nice. Or with 2, it'll have 4 outputs, which will look nice. And then so to set up our backend, it's very simple. We just use the AIR that we imported and we get the backend from it. So it's just a function called get backend, and we specify which one we're using. So today we're using Qasm Simulator. You could also use that state vector thing we mentioned, and I believe there are some other ones as well. But today we'll be doing this, and it's very nicely documented if you're curious about what the other stuff does. So this gives us a backend object, which we then use in our execute function. So the syntax of the execute function, it takes in the circuit you're trying to simulate, the backend you're trying to use to simulate it, and then the amount of times you're trying to simulate it. So in our case, it's called like shots is like the terminology that is common in quantum computing. Just stands for I want to simulate this circuit and get the output 1,000 times. So basically just how many times you want to do it. And then, so this will give you simulate. It'll be an object with a bunch of different data. So this is where coming into plotting our histogram is actually relevant. So it'll have a bunch of like data of like runtime and like results and a bunch of different things that you can parse if you want. But for today, we only really care about the results. So if you do simulate, which is the object that returned from execute, that's all the really complicated data, then do .result to get your results from that simulation, and then get the counts of each individual result. So this will give you the counts of each state and how many times it occurred. And then if you plot it in the histogram, it'll nicely show you the probabilities of everything. So if we go ahead and run this, if we run it over and over again, you'll see these numbers will change because it's accurate and that it's not perfect, right? But this shows us with our two qubit random number generator, there are 4 possible outputs, 0, 0 through 1, 1, just like normal bits. But they have completely random probabilities happening because of the because we're applying that Hadamard gate and then measuring. So it gives that quantum physics true randomness to this. But that's how you would simulate it and then also see your results. So we can run it over and over again and see if we get any really nice. Let's see, I'm just going to keep going. All right, I don't think we're ever going to get a perfect 0.25, 25, whatever. But if we increased the shots a bunch, we would get closer and closer to that. So yeah, is there any questions on either how to simulate your circuit or how to view your simulation results? Okay. So last up we have is actually running on actual hardware. And so that's like the main draw of the IBM quantum experience is that you can actually run it on real quantum computers. And so when you run it, you can get like, you can watch like your live simulation and like all the states and everything. That's not super relevant again today because it involves like more heavy mathematical stuff and background information. We're just interested in getting like truly random results. So you can do that on IBM Quantum Experience. Again, you just have to create an account, which is totally free. And you also have to wait in the queue, which I guess is not free in the sense that it takes time, but otherwise it's free. But because everybody else can also do it, we can actually go back and look back at the homepage. There's a bunch of different quantum computers, all with a different number of qubits. So that limits what kind of programs you can run on them. And there's actually a bunch of different other specifications, like how they're set up, because some qubits are like connected and some are not, and that limits how to optimize your circuit to run on it. But that's, again, not very important for us today. It's very high level. So yeah, we can go ahead and probably try to run one. This one only has 110 jobs. I feel like that wouldn't take that long. Realistically, we're not actually going to really simulate one today because it does take time to wait in that queue, but we're going to go over how to do it. And so to do that, the first thing we can do is we need to, first of all, you need to have an account. So if you're working in the quantum experience, you don't need to do too much. You just need to get the backend provider that allows you to use it on real computers. If you're programming in not the direct quantum experience, you'll have to use your API key from your account, which we're not going to be going over today. But way back up in here at these imports, we imported the stuff to run it on a real computer. So the imports for that, you need to import a module called IBMQ. And then you need to load your account, which is just, if you're logged in to here, it just automatically loads for you. If you're not logged in, you likely have to enter like credentials or something there. I'm not sure, I've never done it outside of this quantum experience. And then we need to get is what's called a provider. This is probably just some high level abstractified thing that actually provides the path to running it on a real computer. So once we have the provider, so we did all this in the initial imports. So if we go back down here, we can actually go ahead and see here. Let's go ahead and comment everything out here and just see, can I do, nope, that didn't work. What about, okay, I'm not sure I'm gonna be able to do this. We're just gonna do it like this. Comment all these lines out really quick so that we can just do provider.backends. And that will show us all the different available quantum computers. I think they change, like some, they go up and down and they add more and less, but this will show them all. And it'll also, you can see like how many jobs there are, or you could just open up this page and see how many jobs there are and like base it on which is least busy. But this tells you the name. And so once you have these names, okay, now we got to uncomment this line and uncomment everything else. Oops. If we go here, okay. So we've seen what the backends look like. So we just need to pick one from here. So when I did my actual simulation, I think IBM Athens was like the least busy. I don't think it's the least busy today. Yeah, it's got 4,000 jobs in it. But we need to get the backend for that actual real computer, which we use with that provider that we imported and set up. And then the actual like process is very, very similar. So before we used IEEE.get backend to get the backend for our simulation. Now we need to get the backend for a real computer. So we have to go through the IBM Q provider. It's still .get backend, and then we need to specify the name of the one we're trying to get to. So in this case, we have IBM Q_Athens. So next up we have, this is a built-in tool to Qiskit called Qiskit Job Watcher, and it'll just pop up a little pop-up over here that shows you where you are in your queue and how long it's expected to take. And then otherwise we have to set up our circuit. So we're setting up again a 2-bit random number generator. And then to actually run it on the real computer, it's very nicely handled in Qiskit, in that you don't really have to change anything. So you have your circuit, you still need to simulate, you still need to give as the input to execute. And then the only thing that changes is your backend here is now the backend we got from the provider. So it's the backend corresponding to the quantum computer IBM Q_Athens, as opposed to the backend we got from the simulation. And then again, we just need to specify how many times we want to simulate it. So for today, we just do 100, we don't need 1,000. And then, so this execute command will actually run it on the quantum computer. It'll enter you into the queue and it'll wait forever until you're done. And then we just like before from the actual simulation, we'll need to get the results, get the counts, and plot them so that we see how it looks. So if we run this, it's oh, let's see. Okay, Qiskit Job Watcher not found. Yeah, you know what? We don't need a Qiskit Job Watcher. Not sure why that is busted, because that's a built-in function. But if we, oh, no, that's not what I wanted to do, sorry. If we try and run it again, there's normally the Qiskit Job Watcher would pop up here. I don't know why it didn't work now. But if we go back to our home page and refresh, I believe we should now have this circuit is being added to the queue. And so it's on the back end of the Athens thing. So we're like super far away. So we're not actually going to wait around for this to go through because it's probably going to, I don't know how long it took when I ran it last time. It was somewhere between like 10 and probably about 30 minutes. Like I said, I left my house while I was waiting for it to go through. But we do have, you can also save your past results. So this is the job ID from the one that I ran before on the same Athens computer. So we should be able to get the old job here. It might not, because the Athens computer might be very busy. I'm not exactly sure how they handle this in the back end of retrieving old jobs. It might be considered like an actual, essentially a simulation again. So we'll give it like 10 seconds, see if it works. And if it doesn't work, we can also go back to that main homepage and look at the old jobs we have, and it should be saved there as well. All right, I think this one's going to take way too long. Let's see, did it add a second queue? How do they handle it in the back end? They don't. Okay, so that's not technically queued, so I don't know why that takes so long then. But if we go to the job, it should show us, yes. So this is the histogram that I ran previously. So the computer stores the results somewhere. I'm no expert on the back end of IBM, but they must in order to be able to display this. So yes. I don't imagine it's like super bad. I imagine IBM has the money to run a server to save all these results, because you're basically just saving like binary numbers pretty much. But this is the results from running it on an actual computer using our quantum circuit with all the Hadamard gates and stuff. I think it'll actually show you. Yeah, this is, so they actually made the circuit, they optimized it a little bit to run on the computer. So instead of applying a Hadamard gate, I guess they applied some equivalent of the Hadamard gate that apparently is easier to run. But it's still the same idea. We're still setting up our two qubits to be in some superposition, and then we're going to measure them. And then that gave us this output here. So this is like actually like real quantum qubit operations. We ran it 1,000 times, generating random numbers, and it gave us a 0, 25.8% of the time, a 1, 24.5% of the time, and so on. So these are truly random numbers, which I think is very cool. But yeah, that's the basics of Qiskit. So we went over today, here, let's go back to the slides, all the way back to the top. So we went over today some necessary imports. By the way, these slides will be out at the end, so if you want to reference these later, but some necessary imports to get started. We went over how to set up a quantum circuit and some basic syntax. We didn't go into everything this package has because it's very, very big and has a ton of functionality. But we went up some basics on how to set up a quantum circuit. We went over how to visualize both our circuit as well as the results. We went over both how to simulate using the IEEE and backends using Qasm Simulator or your state vector simulator. We didn't go over that, but it would just give you the purely theoretical results, or which are not as interesting, as well as how to run it on actual hardware. And otherwise, that's it for today. So are there any questions on anything we covered today? Any parts that were confusing or anything like that? Are those the slides shared, Ishan?
No, that's actually a feedback form. So before anyone else leaves, I noticed people were leaving. If you could fill out that feedback form for us, that would be great.
Do I have to fill it out as well?
If you want to.
Hey, this workshop sucked. This guy who presented didn't know anything. You didn't know how come the Qiskit job washer didn't work. And I have no idea. That's literally the built-in function they give you in the Qiskit library. And it was like, nah, son. But yeah, otherwise, that was all we have for today. And here are some resources. Again, we will be sending out the slides. So here's the link to the quantum experience. Here is a very cool summer Qiskit course that they just like offer for free. You could just watch all the videos and learn all you could possibly fathom. This is like the intro, I think. And also here's the direct link. Let's click on this one. This is the direct link to actual Qiskit. So you can actually like develop Qiskit plugins and functionality if you want.
Maybe we can fix that function for them.
Yeah, I got it. I'm so good at programming, dude. Easy. All right. So yeah, how many people do we have left here? I believe besides the people that helped plan this workshop, we have Ishan and Daniel. So, or
Two Daniels.
Two Daniels.
And a Kevin.
Kevin helped plan.
Oh.
So yeah, slowly trickled out. Hopefully everybody stayed to see the actual programming.
We had like 12 people, like when you started it, and then like 11 people, and then
slowly downwards.
Yeah, 14 was our peak.
Cool.
Oh, I didn't notice the 14. Oh well, they'll watch the recording, right?
Well,
Yeah,
definitely, yeah.
We'll shove it down their gullets.
Is it still recording?
It can be not. Hold on. How do I?